Welcome to another video by Training Made Clear on the Imperial and the Metric System, and today's lesson will be lesson number 7 on flow mass. We have two systems that affect us all every day of our lives in the Imperial and the Metric Systems, and they are shown in the 8 lessons below. So today we're talking about volumetric flow versus mass flow. Definition, plain and technical. Volumetric flow rate Q, the definition, the volume of fluid passing a point per unit time, where Q is the flow rate, how fast something flows, V is the volume, how much fluid, and T is time, how long it takes. Mass flow rate is an M with a dot on top. The definition, the mass fluid passing a point per unit time, where M with a dot is the flow rate, how fast the mass is flowing. M is a mass, how much matter, and T is time, how long it takes. In the diagram on the right hand side we see the formula. Mass flow is equal to A times rho times V, where M is the mass flow rate in kilograms or pounds, and A is the cross-sectional area in meters squared or foot squared, and rho is the density in kilograms per cubic meter or pounds per cubic foot. And V is the velocity in meters per second or feet per second. The equation for mass flow rate is M with a dot is equal to A times rho times V. It is a fundamental relationship in fluid mechanics. Here is a clear explanation. What it means. It tells you how much mass of fluid passes a point per unit time. Mass flow rate answers the question, how many kilograms or pounds of fluid pass through this pipe every second? The symbols explained. M with a dot is mass flow rate, and it means mass per unit time, measured in kilograms per second or pounds per second. A is the area, the cross-sectional area of the pipe, measured in meters squared or foot squared. Rho is the density, mass per unit volume of the liquid, measured in kilograms per cubic meter or pounds per cubic foot. And V is the velocity, the average flow speed of the fluid, measured in meters per second or feet per second. Why the formula works. Volume flowing each second, volume flow rate is Q is equal to A times V, area times velocity, which is equal to volume per second. Convert volume to mass using density. Since density is rho equals mass divided by volume, then mass is equal to rho times volume. If you combine them, then the mass flow rate, rho times Q equals rho times area times velocity. Practical example, water flowing in a pipe. Pipe diameter is 0.1 meter. The area equals pi r squared, which equals to pi times 0.05 square, which equals to 0.00785 meters squared. The density is rho of water, which is equal to 1,000 kilograms per cubic meter. And velocity V is 2 meters per second. If we now calculate with the formula, we get mass flow rate equals 0.00785 times 1,000 times 2, which will equal to 15 kilograms per second. So 15 kilograms of water flows every second. Key insight: if the area increases, mass flow increases. If velocity increases, mass flow increases. If density increases, mass flow increases. That's why gases with low density usually have a much lower mass flow than liquids for the same pipe and same speed. Where this formula is used, m with a dot being mass flow rate equals area times density times velocity. You use it in pipe flow calculations, ventilation systems, pumps and compressors, nozzles and jets, flow meters, example velocity base meters like pitot tubes. Units comparison. If we look at the difference between the metric and the imperial, under volumetric flow, under metric it's meter cube per second or liters per second or meter cubed per hour. For imperial, volumetric flow will be feet cubed per second, cubic feet per minute, or gallons per minute. Mass flow, kilogram per second for metric and kilogram per hour for metric, whereas imperial is pounds per second and pounds per minute. The crucial relationship between volumetric flow rate Q and mass flow rate M. M is equal to rho times Q, where m dot is the mass flow, rho is the fluid density, and Q is the volumetric flow. Density links volume to mass. Visual comparison. Volumetric flow Q measures space. It's affected by density and changes with T and P. T and P mean temperature and pressure in gases. Mass flow, it measures matter. It's independent of density and conserved in system. Behavior in liquids versus gases. Liquids is density constant. Volumetric flow is proportional to mass flow. In gases, density varies with pressure and temperature. It's the same volumetric flow is not equal to the same mass flow. Same system, different view. Gas example. Here's gas flowing in a pipe. If you have high pressure, you have small volume but the same mass. If you have low pressure, you have large volume, same mass. Mass flow stays constant, volumetric flow changes. Here's a worked example for water where mass flow is equal to rho times Q, where m is the mass flow, rho is the fluid density, Q is the volumetric flow. For Q, it is given that the speed is 0.01 meter cube per second, where the density is 1,000 kilograms per cubic meter. The mass flow is equal to 1,000 times 0.01, which will equal 10 kilograms per second. Here is a worked example for air. The given Q is equal to 1 meter cube per second, and rho, the density, is 1.2 kilograms per cubic meter. And here, the mass flow will be equal to 1.2 kilograms per second. If pressure halves, density halves. Mass flow halves at the same time. That's Q. Measurement methods. Flow type and the instruments that will be used. Flow type volumetric, you'll use the instruments Orifice, turbine, or ultrasonic. For mass flow, you would use the Coriolis or thermal mass temperature instruments. When to use which? In the use case, pipe sizing, pump selection, and so forth, this is where you would use the different types of measurements. For pipe sizing, you use volumetric. For pump selection, you use volumetric. For chemical reactions, you'd use mass. Combustion, you'd use mass. Building gases, mass. And HVAC and air balance is volumetric. Common mistakes important. Assuming volumetric flow uniquely defines how much stuff is flowing. Mass flow defines the actual amount of matter. We have a summary table where you have the different aspects and you're comparing volumetric flow to mass flow. So the aspect, the symbol for volumetric flow is Q. For mass flow, it is M with a dot. What it measures, for volumetric, it's space. For mass flow, it's matter. Depends on density. For volumetric flow, yes, and for mass flow, no. Conserved, volumetric, no gases. For mass flow, yes. Most intuitive for liquids, for volumetric flow, and gases, energy, for mass flow. Here's a one-line takeaway. Volumetric flow tells you how much space flows per time. Mass flow tells you how much matter flows per time. I hope you found this video informative and that it's taught you the difference between the two Imperial and Metric systems. So if you like it, please show that you like it, subscribe, share, comment and follow, and thank you for watching.